Indeed, a good afternoon to all of you. I must ask also how the quiz was. How was the quiz, guys? Quiz on mechanical properties of matter. How was it?
It was difficult.
It was quite tricky.
Anyone to ask one of the tricky questions? Anyone who can remember one of the tricky questions?
Elasticity. Let me just send it. I mean, not elasticity. Not elasticity. What's that? Ductility.
Ductility?
Yes.
There was even a question on ductility.
Yes.
Anyway, we might discuss it in the group. So if you have screenshots of that question,
it was there, and it was tricky.
Okay, so if you have questions, screenshots on that question, on some questions, you can send them in the group and then we can discuss them. Today, let us look at impulse. So we did momentum and collision. We looked at momentum and collision, but we didn't look at questions on impulse. Okay, we didn't look at questions on impulse. So today we just want to appreciate the concept of impulse, and it won't be a very long class, it will be a very short one. So I hope you can catch up as quickly as possible. But I guess we know the classical definition of impulse is just the change of momentum, right? Impulse, change in momentum. Are we together?
Yes, sir.
Is this a very strange, I'm sure it's not a very strange concept to you, right? Do I need to like further explain it, derive the equations, or do we all have at least some small understanding of impulse?
Yes.
Somehow.
Yes.
Okay. Let's see if I can try and explain a bit about impulse. So having had looked at momentum, all right, we know that momentum is simply, mass times velocity. When we are looking at momentum, it is mass times velocity. Now, for example, if you have been told that a ball or any object of a certain mass, right, is moving in a certain direction, and then that object of a certain mass, all right, changes its velocity and maybe changes its direction or slows down or speeds up, all right. If we find that a mass, all right, m, has a certain velocity, now the velocity which it has changes, all right, then we'll know that that change in velocity, because it's not only the velocity, because mass doesn't change, all right. If let me say if Muvanga has 2 kg, oh no, she doesn't have 2 kg, she probably has 55 kg, all right. That's an approximation, 50 to 55 kg. So if Muvanga has about 50 kg where she's sitting right now, if she starts running, will her mass change? Will she maybe have 40 kg?
No.
She will maintain her mass, right?
Yes.
Awesome. So we are saying that mass doesn't change. So when momentum is changing, what changes?
The velocity.
Awesome, awesome. So actually, what I could have even written, just a quick one. What I could have even written is, if we have momentum like the way it is, like that, all right? We could also say that it is equals to mass times, all right, in the brackets, all right? Remove this mass here, and then in the brackets, we can remove it and show that the velocity is the only thing that changes, all right? All right, so we see that impulse is just trying to measure, all right? We are trying to measure by how much has this object changed its momentum, all right? Sometimes, let me even give an example in terms of impulse, all right? So let me give an example of a ball in a perfectly elastic collision, all right? This is a wall, right? And then this ball is moving towards this wall like that at maybe 2 meters per second, all right? And then after hitting the wall, it goes back with again 2 meters per second, all right? So let me ask, has the momentum of this ball changed or not? This ball goes back, it hits the wall. This ball hits the wall, moving at 2 meters per second, but then it goes back with that same velocity backward. Has the momentum changed or not?
Has not changed.
Okay. What do the others say?
I think it has changed.
Okay. The person who said momentum has not changed, why do you say momentum has not changed?
I think here, since you said that the velocity supposed changes when the momentum changes, but here the velocity is maintained, which is 2 meters per second.
Awesome.
So and the mass, you say the mass is constant. So when you multiply both, you find same momentum.
Okay. Okay. So Simbarashe, you said the momentum will change. Why do you say so?
I think so because the velocity changes direction. So since velocity is a vector quantity, so the momentum is also supposed to change.
Awesome. Awesome. So I guess Simbarasha has gotten it correct. So this velocity here, which we are pointing in this direction, it is positive 2 meters per second. But this velocity, which is pointing in that direction, it is negative 2 meters per second, all right? So because the sign has changed, this velocity and that velocity is not the same. Velocity has changed. And when velocity changes, momentum of that body will change because the mass is maintained. So the point of interest is the velocity, all right? And then if we can be able to find the final velocity and the initial velocity, we can be able to compute impulse of an object. And then, of course, what we are saying here is just that momentum is the change is mass times the change in velocity, all right? So what we have in the bracket here is just the change in velocity. So impulse is just mass times the change in velocity. And we also know that one thing that you should also know is that for momentum to change, we have to apply a force. All right. This is even coming from Newton's first law of motion. All right. In Newton's first law of motion, we are told that an object will continue in the state of rest or in a motion. So an object will continue in its state of motion unless an external force is what? Applied to it. So if an object is moving at 2 meters, 2 meters per second, this object will continue moving at the same velocity unless we introduce a what? A force. So if we see that the velocity has changed, like the way we have seen, the ball hitting the wall ends up having its velocity changing, meaning the wall has exerted some force on this ball to make it change its velocity. So if we can also find our impulse by just knowing the force that this wall exerts on this ball and the time of contact. All right. So we know that when the ball hits the wall, it doesn't just hit and then in no time goes back. There is a small amount of time. Sometimes it may even be in milliseconds. All right. The point of contact when the ball hits the wall, all right, in a small fraction of a second, it will return back in its opposite, the direction which it was coming from. So we see that time in contact, we also, if we can be able to measure that time, we multiply it by the force, we can be able to know our change in we can be able to know our impulse like that. And we are also saying that with this, we can also extend it that if we can put, divide throughout by t, so that we have t here where there is impulse, we know that our impulse is mass times velocity final minus mass times velocity initial. If we divide it by the time, sometimes you will see in other literatures, they will say change in time. So the change in time. If we can be able to divide our impulse by our change in time, we can be able to find the force that has caused this change in momentum. Are we together?
Yes.
Yes.
Awesome, awesome. Simbarash, you have a question?
Yes.
Yes, sir.
Mm-hmm.
I didn't understand what's the change in time again. Which time are we talking about?
The time that I'm talking about is, I'm giving an example with this wall and this scenario that I've shown here. If a ball is moving towards this wall and when it hits the wall, all right, when it hits the wall, you don't expect it to return back in no time. No, that's not the case. You expect this ball to spend some time on the wall before going back. All right. So if we have this wall and the ball, that time with which the ball is in contact with this force, because we know that the wall is the one which is exerting the force. So that time with which the ball is in contact with this force is this time. Sometimes it's usually a very short period of time. So when you throw a ball at a wall, that ball will spend some time on the wall, maybe the tiny or the fraction of a second, but it's still time, and then it will go back where it is coming from. So the time that we are talking about is the time with which the ball makes in contact with the force. All right, this force, all right, it could be anything. It could be your hands. Sometimes when you are throwing a stone with your hands, you spend some time with that stone in your hands, not so. So when you're trying to swing a stone to throw at someone, that stone, the time that that stone will be in your hands is this time. So you are exerting some force on that ball as it is in your hands. And when you let go of it, we stop counting the time. So that is a time. But sometimes in a case of a war, the time may be even very, very short. So you find that it will just bounce maybe for 2 milliseconds or a very, very short time. But then it's still time. The time that the object makes contact with the force is this time that we are talking about here. Is that okay, Mr. Simbarasha?
Yes, sir.
Awesome. So we shall not go so much in the theory of looking at. In fact, we have already gone through the theory of looking at impulse. Now, what we need to do is to look at some examples. So may we have? Okay, Eunice, good to have you. Though you were a bit late, good to have you. And could you help us read the question that we have here?
All right, thank you, sir. In a crash test, a car of mass 1.50 multiplied by 10 exponential 3 collides with a wall and rebounds as in figure 6.4. I don't know if this is acceleration.
No,
The
this
initial
is just telling us the figure where it is. For us, it is on the next side. It's on the next side of it.
Okay. The initial and final velocities of the car are V initial is equals to negative 15.0 meter per second, and V final is equals to 2.60 meter per second, respectively. If the collision lasts for 0.150 seconds, find A, the impulse delivered to the car due to the collision, and the size and direction of the average force exerted on the car.
Awesome. Awesome. All right. That's wonderful. Now, again, I always, in fact, during your quiz, I just hope and pray that you guys were reading your questions more than twice. All right. Sometimes when you read the question for the first time, you don't get what they are saying. Read it again, and read it again. I always emphasize, if you have 5 minutes to solve your question, make sure the 4 minutes you use it to understand the question and the 1 minute you use it to solve the question. So when you envision, of course, we'll look at the diagram. When you envision a car with a certain mass colliding, meaning it hits in a wall, and then it rebounds. Rebounding, I'm sure you guys know what the word rebounding is. Rebounding is just to bounce back. So if it was going in this direction, it bounces back and starts going in the other direction, the opposite direction. That's rebounding. So the initial velocity with which it was going this direction, of course, let's look at we'll look at the diagram. Of course, the initial velocity with which it was going in this direction is this. So since it is going in this direction, obviously it will have a negative velocity. But then the final velocity, since it is going in this direction, it will have that positive velocity. So they are telling us to calculate the what? The impulse. Now, how do we calculate this impulse? All right. So we've been given the information. We have also been given the time with which the collision lasts. So meaning, since we have seen that there's a change in velocity, in fact, I'm sure you can even see here that I've been indicated average force. So since there is a change in velocity, there should be a force that was applied, all right? And then that force was in contact with the car for about 1.5 seconds. So this is what they mean by saying if the collision lasts for 0.15 seconds. That means this force was in contact with the car for about 1.5 seconds, 0.15 seconds. And yeah, so the size and direction of the force, we need to calculate that. So let's look at the diagram. Let's look at, so now we have the diagram here. All right, we have the mass of this car. It's moving in this direction at that velocity. And then, of course, this is the initial velocity. This is the final velocity. I should have indicated it as final like that. And then this is the time. All right, are we together?
Yes.
Yes, sir.
Yes, we should be saying so that we know that we are together. So always make sure that the diagram is there. If the diagram is not there, you draw it yourself. So the car hits the wall and then it rebounds. All right. After hitting the wall, it rebounds. Of course, there is some deformation on the car there. So now the first question is saying, find the calculate the impulse delivered to the car due to the collision. So we all know that impulse is the change in momentum. All right. And the change in momentum is just, since we are dealing with one mass, we know that mass, sometimes you may have two masses. So you may consider those two masses. But in this case, we just have one mass, one car. And the mass of that car is presented like this. So we can write the formulas as, velocity final minus velocity initial, we multiply it by the mass, all right? We have the mass given, and we have the velocity final. So we always start with velocity final minus the velocity initial. The velocity initial was negative. So you put a minus, and then in the brackets, you put the sign of the velocity. So the temptation will be for you to write the 2.6, the 2.6, you write it minus 15. All right, that would be a bad thing because this 15 is not just 15, it is also a negative. So you include the negative like that, so that when these negatives will cancel out, you have a positive, and when you multiply throughout, you get this to be your impulse. Are we okay there?
Yes, sir.
Yes, sir. Yes, sir.
Awesome. So any question that comes on impulse, you guys should not fail to solve it. And sometimes they will not mention the word impulse. All right. They will not mention the word impulse, but you should have this type of thinking on your fingertips. I think as a student at the university, like I always say, don't expect things to be like the way they were in high school, where they'll ask you definite things where you can just plug in the formula and out comes the answer. As a student, as a university student, you need to think. Sometimes they will not use the word impulse. They will just use information that should click in your mind, that I think here they are talking about the concept of impulse, because the impulse is just changing momentum. All right, changing momentum. And changing momentum, usually if it's just one body, it's just simply the change in velocity. All right. So if an object is changing its velocity, you know that the momentum is changing. And you can also use these equations of momentum to be able to resolve any question of an object changing its velocity. So the key is changing velocity. Mass, if mass is maintained and the velocity changes, you know you can use these formulas to be able to find what you are looking for. If what you are looking for is related to impulse, even if they have not used the word impulse. All right. There was a certain question. In fact, let's first, before I even come to certain question, this, awesome. So let's look at part B. Part B. Part B is saying the size and direction of the average force exerted on the car. All right. So force, we know that impulse, which we have just from calculating, is force times time. All right, we can now make T, F, we can now make F the subject of the formula and say that force is equals to impulse over time. All right, we are just from calculating our impulse, and we have our time. The time is how long was the force in contact with the body in question. So that is the time, and then when you divide the two, you get your force like that. Are we together there?
Yes.
Awesome. How many of you know about those cars which have airbags? Airbags. How many of you know those cars?
Yeah, we know them.
Uh-huh.
Is it not that every car has the airbag?
No, not all cars. So not all cars have airbags, all right? Some cars have airbags and some don't. So do you know why they put the airbags there? Easy to increase this time of impact. So if you are moving in a car, all right, you are moving in a car like this, and then it hits into a wall or a tree, all right, let's say it's a tree, it collides, makes an accident, right? So this car, it will stop maybe in a short period of time, maybe in maybe say in 0.00 maybe 5 seconds, just boom, it has stopped, all right, after hitting this tree. Maybe if it's a strong tree, it will stop like that. But then you, the person who is inside here, all right, because of that airbag, you won't stop. You are moving in a car and you are moving at the same velocity with the car. But because the airbag will come out, the airbag will reduce. So it will, even if the car has stopped, you will continue moving for a bit because of this airbag. So that you would deform, you would deflect, or you would deform this airbag. Even when the car has stopped moving, you move a bit in front, the airbag will stop you, but it won't stop you immediately. It will deflect you such that maybe if the time the car stopped was 0.005, it can be 0.1. So that if you increase the time, you reduce the what? The force. Are you seeing this? All right.
Yes, sir.
So let me also ask an example just to help you grasp the concept of impulse. When you are jumping from a certain height to drop down, you just jump with your legs stretched out like that and just hit the ground. When you hit the ground, you curve your legs, not so. When your feet hit the ground, you bend a bit so that even if your feet have stopped moving when they hit the ground, you bend a bit by continuing to move a bit so that you increase the time of stopping. And when you increase the time of stopping, you decrease the force, because this force is the one which is dangerous. If this force is too much, it can damage the car, it can damage you, your body. But if you can increase the time of stopping or the time of the impulse, if you increase it, then you can reduce the force. Have you seen, even in this equation, if this time, for example, if it was 10 seconds, would this force have reduced or increased? Would it have reduced or increased? Anyone, please? Eunice, if we increase the time, will the force increase or reduce?
I think it will reduce.
Awesome. Awesome. So the thing with physics, don't just be interested in the formulas. Let the concept resonate across the four corners of your mind, your cognitives, your perception, your processing power in your head. Let the concept saturate your brain such that no matter how they will phrase the question, you know the concept. And you can even apply it in real life. So that even when you are speaking to someone, they know this person is learned. This person has gone to the university. So from now on, you know that impulse, you know that the force when a collision occurs, if we can find a change in momentum, impulse is the change in momentum. How long did it take for the momentum to change? Is this time? How long did it take for the momentum to change? If we have the change in momentum over how long it took the momentum to change, we can get the force which was delivered. And if we can increase the time, we can reduce the force. And there are many ways. I've talked about the airbags, which are used in cars to increase the time, thereby reducing the force. But the change in momentum is the same. Change in momentum will be maintained, but the force will be reduced. So let's look at an example, another example, especially now, which talks about the car actually hitting into something and coming to stop. So let us have Kaoma Muvanga to help us read this question. Muvanga, could you help us read this question?
Sure. A car of mass 500 kg moving at a velocity of 25 meters per second hits into a tree and comes to a stop. Given that the car deforms by 1.5 meters before coming to a stop, calculate A, the impulse delivered to the tree. B, the force which the tree exerts on the car to stop it.
Awesome. Awesome. So we have a car moving with this velocity, hits into a what? A tree, and then comes to do what? To stop. But the car, you know that when it hits into something, it will deform. So we see that when we measure the deformation is about 1.5, and then it stops like that. So we want to calculate the impulse. We want to calculate the impulse delivered to the tree. All right. So when you hit the tree, obviously there will be change in momentum because it was moving at this velocity, but then it stops. We have not drawn a diagram for now, but I guess you can be able to visualize it. So we have the mass of the car, we have the initial velocity of the car, the final velocity of the car is 0 because it stopped, and the distance is the deformation. It deforms by 1.5, and then for us to find the solution, I don't want us to go to the next, because Zoom is about to end. I don't want us to go to the next to make another meeting. I'm feeling like we can manage to finish up even with this little time that we have. So make sure you follow me closely. So the impulse, to find the impulse delivered to the tree, all we need to do is use the same formula as we have been using. We have the mass and the velocity. We know it came to stop. Initially, it was moving at 25 meters per second. And then when we subtract, when we do this, velocity final minus velocity initial, and multiply it by the mass, we get to find our negative impulse, all right? Meaning the momentum changed negatively, meaning the impulse is negative. So the force, how can we find the force? So the force with which the tree exerts on the car, all right? So this force, we know that it is still impulse divided by time. But what is the time? We're not given the time in the question. How can we find this time? So we know with the physics, we know that distance is equals to initial velocity. I mean, if we have, we can also, I'm sure you know one of the formulas for distance is that the average, in fact, we're supposed to have divided by 2, sorry, by 2 like that. So initial velocity plus final velocity divided by 2, we get our V average. All right, we get our V average, and velocity, the average velocity times the time should be able to give us a distance. And which distance are we using? We're using the deformation. So the car deformed by 1.5. Again, I left out dividing by 2. Yeah, so the average is gotten by the initial velocity, you add it with the final velocity, then you divide it by 2. When you multiply by time, you should get your distance, all right? And then we are saying that if we solve it like this, we can find our time, all right? Because it's the only thing that we don't know. And then solving for our time, we get this as our time. And then putting it back in the formula, we have our impulse, then we have our time. We see that the force that we get is negative, okay? This is how we do questions on impulse. Are we clear? Do we have questions on how to go about such questions? Simbarashe, quickly.
Yes, sir. What is, like, is there any special case where when impulse is negative, it means something?
Is there any special